9. Testing of hypotheses I. Parametric or standard tests of hypotheses. Hypothesis is usually considered as the principal instrument in research. Its main function is to suggest new experiments and observations. In fact, many experiments are carried out with the deliberate object of testing hypotheses. Decision-makers often face situations wherein they are interested in testing hypotheses on the basis of available information and then take decisions on the basis of such testing. In social science, where direct knowledge of population parameters is rare, hypothesis testing is the often used strategy for deciding whether a sample data offers such support for a hypothesis that generalization can be made. Thus, hypothesis testing enables us to make probability statements about population parameters. The hypothesis may not be proved absolutely, but in practice it is accepted if it has withstood a critical testing. Before we explain how hypotheses are tested, through different tests meant for the purpose, it will be appropriate to explain clearly the meaning of a hypothesis and the related concepts for better understanding of the hypothesis testing techniques. What is a hypothesis? Ordinarily, when one talks about hypothesis, one simply means a mere assumption or some supposition to be proved or disproved. But for a researcher, hypothesis is a formal question that he intends to resolve. Thus, a hypothesis may be defined as a proposition or a set of propositions set forth as an explanation for the occurrence of some specified group of phenomena, either asserted merely as a provisional conjecture to guide some investigation or accepted as highly probable in the light of established facts. Quite often, a research hypothesis is a predictive statement capable of being tested by scientific methods that relates an independent variable to some dependent variable. For example, consider statements like the following ones: students who receive counseling will show a greater increase in creativity than students not receiving counseling, or the automobile A is performing as well as automobile B. These are hypotheses capable of being objectively verified and tested. Thus, we may conclude that a hypothesis states what we are looking for, and it is a proposition which can be put to a test to determine its validity. Characteristics of hypothesis. Hypothesis must possess the following characteristics. Hypothesis should be clear and precise. If the hypothesis is not clear and precise, the inferences drawn on its basis cannot be taken as reliable. 2. Hypothesis should be capable of being tested. In a swamp of untestable hypotheses, many a time the research programs have bogged down. Some prior study may be done by researcher in order to make hypothesis a testable one. A hypothesis is testable if other deductions can be made from it, which, in turn, can be confirmed or disproved by observation. 3. Hypothesis should state relationship between variables, if it happens to be a relational hypothesis. 4. Hypothesis should be limited in scope and must be specific. A researcher must remember that narrower hypotheses are generally more testable, and he should develop such hypotheses. Hypothesis should be stated as far as possible in most simple terms so that the same is easily understandable by all concerned. But one must remember that simplicity of hypothesis has nothing to do with its significance. 6. Hypothesis should be consistent with most known facts, i.e., it must be consistent with a substantial body of established facts. In other words, it should be one which judges accept as being the most likely. 7. Hypothesis should be amenable to testing within a reasonable time. One should not use even an excellent hypothesis If the same cannot be tested in reasonable time, for one cannot spend a lifetime collecting data to test it. 8. Hypothesis must explain the facts that gave rise to the need for explanation. This means that by using the hypothesis plus other known and accepted generalizations, one should be able to deduce the original problem condition. Thus, hypothesis must actually explain what it claims to explain. It should have empirical reference. Basic concepts concerning testing of hypotheses. Basic concepts in the context of testing of hypotheses need to be explained. A. Null hypothesis and alternative hypothesis. In the context of statistical analysis, we often talk about null hypothesis and alternative hypothesis. If we are to compare method A with method B about its superiority, and if we proceed on the assumption that both methods are equally good, then this assumption is termed as the null hypothesis. As against this, we may think that the method A is superior or the method B is inferior. We are then stating what is termed as alternative hypothesis. The null hypothesis generally symbolized as H0 and the alternative hypothesis as H. Suppose we want to test the hypothesis that a population mean is equal to the hypothesized mean H100. Then we would say that the null hypothesis is that the population mean is equal to the hypothesized mean 100, and symbolically we can express as H0, H0 100. If our sample results do not support this null hypothesis, we should conclude that something else is true. What we conclude rejecting the null hypothesis is known as alternative hypothesis. In other words, the set of alternatives to the null hypothesis is referred to as the alternative hypothesis. If we accept H0, then we are rejecting H, and if we reject H0, then we are accepting H. For H0 100, we may consider three possible alternative hypotheses as follows: *0. Pause the video to look at the table. The null hypothesis and the alternative hypothesis are chosen before the sample is drawn. The researcher must avoid the error of deriving hypotheses from the data that he collects and then testing the hypotheses from the same data. In the choice of null hypothesis, the following considerations are usually kept in view. A. Alternative hypothesis is usually the one which one wishes to prove, and the null hypothesis is the one which one wishes to disprove. Thus, a null hypothesis represents the hypothesis we are trying to reject, and alternative hypothesis represents all other possibilities. B. If the rejection of a certain hypothesis when it is actually true involves great risk, it is taken as null hypothesis because then the probability of rejecting it when it is true is the level of significance, which is chosen very small. C. Null hypothesis should always be specific hypothesis, i.e., it should not state about or approximately a certain value. Generally, in hypothesis testing we proceed on the basis of null hypothesis, keeping the alternative hypothesis in view. Why so? The answer is that on the assumption that null hypothesis is true, one can assign the probabilities to different possible sample results, but this cannot be done if we proceed with the alternative hypothesis. Hence the use of null hypothesis, at times also known as statistical hypothesis, is quite frequent. B. The level of significance. This is a very important concept in the context of hypothesis testing. It is always some percentage, usually 5%, which should be chosen with great care, thought and reason. In case we take the significance level at 5%, then this implies that H0 will be rejected. 0. H. Table 9.2. When the sampling result, i.e., observed evidence, has a less than 0.05 probability of occurring if H0 is true. In other words, the 5% level of significance means that researcher is willing to take as much as a 5% risk of rejecting the null hypothesis when it, H0, happens to be true. Thus, the significance level is the maximum value of the probability of rejecting H0 when it is true and is usually determined in advance before testing the hypothesis.
C. Decision rule or test of hypothesis. Given a hypothesis H0 and an alternative hypothesis HA, we make a rule which is known as decision rule, according to which we accept H0, i.e., reject HA, or reject H0, i.e., accept HA. For instance, if H0 is that a certain lot is good, there are very few defective items in it, against HA, that the lot is not good, there are too many defective items in it, then we must decide the number of items to be tested and the criterion for accepting or rejecting the hypothesis. We might test 10 items in the lot and plan our decision saying that if there are none or only one defective item among the 10, we will accept H0, otherwise we will reject H0, or accept HA. This sort of basis is known as decision rule. D. Type I and Type 2 errors. In the context of testing of hypotheses, there are basically two types of errors we can make. We may reject H0 when H0 is true, and we may accept H0 when in fact H0 is not true. The former is known as type I error and the latter as type 2 error. In other words, type I error means rejection of hypothesis which should have been accepted, and type 2 error means accepting the hypothesis which should have been rejected. Type I error is denoted by alpha, known as error, also called the level of significance of test, and type 2 error is denoted by beta, known as error. In a tabular form, the said two errors can be presented as follows.
Pause the video to look at the table. The probability of type I error is usually determined in advance and is understood as the level of significance of testing the hypothesis. If type I error is fixed at 5%, it means that there are about 5 chances in 100 that we will reject H0 when H0 is true. We can control type I error just by fixing it at a lower level. For instance, if we fix it at 1%, we will say that the maximum probability of committing type I error would only be 0.01. But with a fixed sample size, n, when we try to reduce type I error, the probability of committing type 2 error increases. Both types of errors cannot be reduced simultaneously. There is a trade-off between two types of errors, which means that the probability of making one type of error can only be reduced if we are willing to increase the probability of making the other type of error. To deal with this trade-off in business situations, decision-makers decide the appropriate level of type I error by examining the costs or penalties attached to both types of errors. If type I error involves the time and trouble of reworking a batch of chemicals that should have been accepted, whereas type 2 error means taking a chance that an entire group of users of this chemical compound will be poisoned, then 0. In such a situation, one should prefer a type I error to a type 2 error. As a result, one must set very high level for type I error in one's testing technique of a given hypothesis. Hence, in the testing of hypothesis, one must make all possible effort to strike an adequate balance between type I and type 2 errors. E. Two-tailed and one-tailed tests. In the context of hypothesis testing, these two terms are quite important and must be clearly understood. A two-tailed test rejects the null hypothesis if, say, the sample mean is significantly higher or lower than the hypothesized value of the mean of the population. Such a test is appropriate when the null hypothesis is some specified value and the alternative hypothesis is a value not equal to the specified value of the null hypothesis. Symbolically, the two-tailed test is appropriate when we have H0 Thus, in a two-tailed test, there are two rejection regions *, one on each tail of the curve, which can be illustrated as under. Pause the video to look at the figure. Mathematically, we can state acceptance region A, Z rejection region R, Z 1.96, 1.96 if the significance level is 5% and the two-tailed test is to be applied, the probability of the rejection area will be 0.05, equally splitted on both tails of the curve as 0.025, and that of the acceptance region will be 0.95 as shown in the above curve. If we take 100 and if our sample mean deviates significantly from 100 in either direction, then we shall reject the null hypothesis, but if the sample mean does not deviate significantly from, in that case we shall accept the null hypothesis. But there are situations when only one-tailed test is considered appropriate. A one-tailed test would be used when we are to test, say, whether the population mean is either lower than or higher than some hypothesized value. For instance, if our H0 and H0, then we are interested in what is known as left-tailed test, wherein there is one rejection region only on the left tail, which can be illustrated as below. Pause the video to look at the figure. Mathematically, we can state acceptance region A, Z1.645, rejection region R, Z1.645. If R100 and if our sample mean deviates significantly from 100 in the lower direction, we shall reject H0, otherwise we shall accept H0 at a certain level of significance. If the significance level in the given case is kept at 5%, then the rejection region will be equal to 0.05 of area in the left tail as has been shown in the above curve. In case R H0, H and H0, we are then interested in what is known as one-tailed test, right tail, and the rejection region will be on the right tail of the curve as shown below. Pause the video to look at the figure. Mathematically, we can state acceptance region A, Z 1.645, rejection region A, Z 1.645. If R100 and if our sample mean deviates significantly from 100 in the upward direction, we shall reject H0, otherwise we shall accept the same. If in the given case the significance level is kept at 5%, then the rejection region will be equal to 0.05 of area in the right tail as has been shown in the above curve. It should always be remembered that accepting H0 on the basis of sample information does not constitute the proof that H0 is true. We only mean that there is no statistical evidence to reject it, but we are certainly not saying that H0 is true, although we behave as if H0 is true. Procedure for hypothesis testing. To test a hypothesis means to tell, on the basis of the data the researcher has collected, whether or not the hypothesis seems to be valid. In hypothesis testing, the main question is whether to accept the null hypothesis or not to accept the null hypothesis. Procedure for hypothesis testing refers to all those steps that we undertake for making a choice between the two actions, i.e., rejection and acceptance of a null hypothesis. The various steps involved in hypothesis testing are stated below. I. Making a formal statement. The step consists in making a formal statement of the null hypothesis, H0, and also of the alternative hypothesis, H. This means that hypothesis should be clearly stated, considering the nature of the research problem. For instance, Mr. Mohan of the Civil Engineering Department wants to test the load-bearing capacity of an old bridge which must be more than 10 tons. In that case, he can state his hypotheses as under. Null hypothesis H0, 10 tons. Alternative hypothesis H, 10 tons. Take another example. The average score in an aptitude test administered at the national level is 80. To evaluate a state's education system, the average score of 100 of the state's students selected on random basis was 75. The state wants to know if there is a significant difference between the local scores and the national scores. In such a situation, the hypotheses may be stated as under. Null hypothesis H0, 80. Alternative hypothesis H, 80. The formulation of hypotheses is an important step which must be accomplished with due care in accordance with the object and nature of the problem under consideration. It also indicates whether we should use a one-tailed test or a two-tailed test. If H is of the type greater than or of the type lesser than, we use a one-tailed test, but when H is of the type whether greater or smaller, then we use a two-tailed test. 2. Selecting a significance level. The hypotheses are tested on a predetermined level of significance and as such the same should be specified. Generally, in practice, either 5% level or 1% level is adopted for the purpose. The factors that affect the level of significance are A. The magnitude of the difference between sample means, B. The size of the samples, C. The variability of measurements within samples, and D. Whether the hypothesis is directional or non-directional. A directional hypothesis is one which predicts the direction of the difference between, say, means. In brief, the level of significance must be adequate in the context of the purpose and nature of inquiry. 3. Deciding the distribution to use. After deciding the level of significance, the next step in hypothesis testing is to determine the appropriate sampling distribution. The choice generally remains between normal distribution and the t-distribution. The rules for selecting the correct distribution are similar to those which we have stated earlier in the context of estimation. 4. Selecting a random sample and computing an appropriate value. Another step is to select a random samples and compute an appropriate value from the sample data concerning the test statistic utilizing the relevant distribution. In other words, draw a sample to furnish empirical data. Calculation of the probability. One has then to calculate the probability that the sample result would diverge as widely as it has from expectations if the null hypothesis were in fact true. 6. Comparing the probability. Yet another step consists in comparing the probability thus calculated with the specified value for the significance level. If the calculated probability is equal to or smaller than the value in case of one-tailed test and 2 in case of two-tailed test, then reject the null hypothesis, i.e., accept the alternative hypothesis, but if the calculated probability is greater, then accept the null hypothesis. In case we reject H0, we run a risk of, at most the level of significance, committing an error of type I, but if we accept H0 then we run some risk, the size of which cannot be specified as long as the H0 happens to be vague rather than specific, of committing an error of type 2. Flow diagram for hypothesis testing. The above stated general procedure for hypothesis testing can also be depicted in the form of a flow chart for better understanding as shown in Fig. 9.4. Pause the video to look at the figure measuring the power of a hypothesis test. As stated above, we may commit type I and type 2 errors while testing a hypothesis. The probability of type I error is denoted as the significance level of the test and the probability of type 2 error is referred to as. Usually the significance level of a test is assigned in advance, and once we decide it, there is nothing else we can do about. But what can we say about? We all know that hypothesis test cannot be foolproof. Sometimes the test does not reject H0 when it happens to be a false one, and this way a type 2 error is made. But we would certainly like that the probability of accepting H0 when H0 is not true to be as small as possible. Alternatively, we would like that 1, the probability of rejecting H0 when H0 is not true to be as large as possible. If 1 is very much nearer to unity, i.e., nearer to 1.0, we can infer that the test is working quite well, meaning thereby that the test is rejecting H0 when it is not true, and if 1 is very much nearer to 0.0, then we infer that the test is poorly working, meaning thereby that it is not rejecting H0 when H0 is not true. Accordingly, 1 value is the measure of how well the test is working, or what is technically described as the power of the test. In case we plot the values of 1 for each possible value of the population parameter, say the true population mean, for which the 0 is not true, alternatively the Ha is true, the resulting curve is known as the power curve associated with the given test. Thus, power curve of a hypothesis test is the curve that shows the conditional probability of rejecting H0 as a function of the population parameter and size of the sample. The function defining this curve is known as the power function. In other words, the power function of a test is that function defined for all values of the parameters, which yields the probability that H0 is rejected, and the value of the power function at a specific parameter point is called the power of the test at that point. As the population parameter gets closer and closer to hypothesized value of the population parameter, the power of the test, i.e., 1 must get closer and closer to the probability of rejecting H0 when the population parameter is exactly equal to hypothesized value of the parameter. We know that this probability is simply the significance level of the test, and as such, the power curve of a test terminates at a point that lies at a height of the significance level directly over the population parameter. Closely related to the power function, there is another function which is known as the operating characteristic function, which shows the conditional probability of accepting H0 for all values of population parameters for a given sample size, whether or not the decision happens to be a correct one. If power function is represented as H and operating characteristic function as L, then we have L is equal to 1H. However, one needs only one of these two functions for any decision rule in the context of testing hypotheses. Tests of hypotheses. As has been stated above, that hypothesis testing determines the validity of the assumption, technically described as null hypothesis, with a view to choose between two conflicting hypotheses about the value of a population parameter. Hypothesis testing helps to decide on the basis of a sample data whether a hypothesis about the population is likely to be true or false. Statisticians have developed several tests of hypotheses, also known as the tests of significance, for the purpose of testing of hypotheses, which can be classified as A. Parametric tests or standard tests of hypotheses, and B. Non-parametric tests or distribution-free test of hypotheses. Parametric tests usually assume certain properties of the parent population from which we draw samples. Assumptions like observations come from a normal population, sample size is large, assumptions about the population parameters like mean, variance, etc. must hold good before parametric tests can be used. But there are situations when the researcher cannot or does not want to make such assumptions. In such situations, we use statistical methods for testing hypotheses, which are called non-parametric tests because such tests do not depend on any assumption about the parameters of the parent population. Besides, most non-parametric tests assume only nominal or ordinal data, whereas parametric tests require measurement equivalent to at least an interval scale. As a result, non-parametric tests need more observations than parametric tests to achieve the same size of type I and type 2 errors. 4 We take up in the present chapter some of the important parametric tests, whereas non-parametric tests will be dealt with in a separate chapter later in the book. Important parametric tests. The important parametric tests are 1. Z-test, 2. T-test, 3. T-test, and 4. F-test. All these tests are based on the assumption of normality, i.e., the source of data is considered to be normally distributed. In some cases, the population may not be normally distributed, yet the tests will be applicable on account of the fact that we mostly deal with samples and the sampling distributions closely approach normal distributions. Z-test is based on the normal probability distribution and is used for judging the significance of several statistical measures, particularly the mean. The relevant test statistic, Z, is worked out and compared with its probable value, to be read from table showing area under normal curve, at a specified level of significance for judging the significance of the measure concerned. This is a most frequently used test in research studies. This test is used even when binomial distribution or t-distribution is applicable on the presumption that such a distribution tends to approximate normal distribution as n becomes larger. Z-test is generally used for comparing the mean of a sample to some hypothesized mean for the population in case of large sample, or when population variance is known. Z-test is also used for judging the significance of difference between means of two independent samples in case of large samples, or when population variance is known. Z-test is also used for comparing the sample proportion to a theoretical value of population proportion, or for judging the difference in proportions of two independent samples when n happens to be large. Besides, this test may be used for judging the significance of median, mode, coefficient of correlation, and several other measures. T-test is based on t-distribution and is considered an appropriate test for judging the significance of a sample mean or for judging the significance of difference between the means of two samples in case of small samples when population variance is not known, in which case we use variance of the sample as an estimate of the population variance. In case two samples are related, we use paired t-test, or what is known as difference test, for judging the significance of the mean of difference between the two related samples. It can also be used for judging the significance of the coefficients of simple and partial correlations. The relevant test statistic, t, is calculated from the sample data and then compared with its probable value based on t-distribution, to be read from the table that gives probable values of t for different levels of significance for different degrees of freedom, at a specified level of significance for concerning degrees of freedom for accepting or rejecting the null hypothesis. It may be noted that t-test applies only in case of small samples when population variance is unknown. T-test is based on chi-square distribution and as a parametric test is used for comparing a sample variance to a theoretical population variance. F-test is based on F distribution and is used to compare the variance of the two independent samples. This test is also used in the context of analysis of variance, ANOVA, for judging the significance of more than two sample means at one and the same time. It is also used for judging the significance of multiple correlation coefficients. Test statistic, F, is calculated and compared with its probable value, to be seen in the F ratio tables for different degrees of freedom for greater and smaller variances at specified level of significance, for accepting or rejecting the null hypothesis. The table on pages 198 to 201 summarizes the important parametric tests along with test statistics and test situations for testing hypotheses relating to important parameters, often used in research studies in the context of one sample and also in the context of two samples. We can now explain and illustrate the use of above stated test statistics in testing of hypotheses. Hypothesis testing of means. Mean of the population can be tested presuming different situations, such as the population may be normal or other than normal, it may be finite or infinite, sample size may be large or small, variance of the population may be known or unknown, and the alternative hypothesis may be two-sided or one-sided. Our testing technique will differ in different situations. We may consider some of the important situations. 1. Population normal, population infinite, sample size may be large or small but variance of the population is known, may be one-sided or two-sided. In such a situation, z-test is used for testing hypothesis of mean and the test statistic z is worked are as under. _____. 2. Population normal, population finite, sample size may be large or small but variance of the population is known, may be one-sided or two-sided. In such a situation, z-test is used and the test statistic z is worked out as under, using finite population multiplier. _____. 3. Population normal, population infinite, sample size small and variance of the population unknown, may be one-sided or two-sided. In such a situation, t-test is used and the test statistic t is worked out as under. Pause the video to look at the formula. 4. Population normal, population finite, sample size small and variance of the population unknown, and may be one-sided or two-sided. In such a situation, t-test is used and the test statistic t is worked out as under, using finite population multiplier. Pause the video to look at the formula and table. Pause. Again. Pause. Again. Pause. Again. And sigma is equal to or 5. Population may not be normal but sample size is large, variance of the population may be known or unknown, and may be one-sided or two-sided. In such a situation, we use z-test and work out the test statistic z as under. Z equals 2. This applies in case of infinite population when variance of the population is known but when variance is not known, we use S in place of P in this formula. Z equals 2. This applies in case of finite population when variance of the population is known, but when variance is not known, we use S in place of P in this formula. Hypothesis testing for differences between means. In many decision situations, we may be interested in knowing whether the parameters of two populations are alike or different. For instance, we may be interested in testing whether female workers earn less than male workers for the same job. We shall explain now the technique of PS. Hypothesis testing for differences between means. The null hypothesis for testing of difference between means is generally stated as H0, 1, 2, where 1 is population mean of one population and 2 is population mean of the second population, assuming both the populations to be normal populations. Alternative hypothesis may be of not equal to or less than or greater than type as stated earlier, and accordingly we shall determine the acceptance or rejection regions for testing the hypotheses. There may be different situations when we are examining the significance of difference between two means, but the following may be taken as the usual situations. 1. Population variances are known or the samples happen to be large samples. In this situation, we use z-test for difference in means and work out the test statistic z as under z equals 2. In case P1 and P2 are not known, we use S and S respectively in their places 1 to calculating. Pause the video to look at the formula. Two samples happen to be large but presumed to have been drawn from the same population whose variance is known. In this situation, we use z-test for difference in means and work out the test statistic z as under z equals 2. In case is not known, we use combined standard deviation of the two samples, 1.2 in its place calculating. x12 equals 2. 3 samples happen to be small samples and population variances not known but assumed to be equal. In this situation, we use t-test for difference in means and work out the test statistic t as under t equals 2. With df is equal to n1 plus n2, 2. Alternatively, we can also state t equals 2. With df is equal to n1 plus n2, 2. NPQ. Hypothesis testing for comparing to related samples. Paired t-test is a way to test for comparing to related samples involving small values of n that does not require the variances of the two populations to be equal, but the assumption that the two populations are normal must continue to apply. For a paired t-test, it is necessary that the observations in the two samples be collected in the form of what is called matched pairs, i.e., each observation in the one sample must be paired with an observation in the other sample in such a manner that these observations are somehow matched or related, in an attempt to eliminate extraneous factors which are not of interest in test. 5. Such a test is generally considered appropriate in a before and after treatment study. For instance, we may test a group of certain students before and after training in order to know whether the training is effective, in which situation we may use paired t-test. To apply this test, we first work out the difference score for each matched pair, and then find out the average of such differences, D, along with the sample variance of the difference score. If the values from the two matched samples are denoted as she and ye and the differences by D is equal to she, ye, then the mean of the differences I, D bar equals to sigma D I upon N. And the variance of the differences or. Why do so Tito look at the formula? Assuming the said differences to be normally distributed and independent, we can apply the paired t-test for judging the significance of mean of differences and work out the test statistic T as under. Pause again. Diff is equal to standard deviation of differences. N is equal to number of matched pairs. This calculated value of T is compared with its stable value at a given level of significance as usual for testing purposes. We can also use Sandler's A-test for this very purpose as stated earlier in Chapter 8. Hypothesis testing of proportions. In case of qualitative phenomena, we have data on the basis of presence or absence of an attributes. With such data, the sampling distribution may take the form of binomial probability distribution whose mean would be equal to NP and standard deviation equal to, where P represents the probability of success, Q represents the probability of failure such that P plus Q is equal to 1 and N, the size of the sample. Instead of taking mean number of successes and standard deviation of the number of PQN successes, we may record the proportion of successes in each sample, in which case the mean and standard deviation or the standard error of the sampling distribution may be obtained as follows. Mean proportion of successes NP, NP, and standard deviation of proportion of successes. In N is large, the binomial distribution tends to become normal distribution, and as such for proportion testing purposes we make use of the test statistic Z as under. Z equals to, where P is the sample proportion. For testing of proportion, we formulate H0 and Ha and construct rejection region, presuming normal approximation of the binomial distribution for a predetermined level of significance, and then may judge the significance of the observed sample result. The following examples make all this quite clear. Hypothesis testing for difference between proportions. If two samples are drawn from different populations, one may be interested in knowing whether the difference between the proportion of successes is significant or not. In such a case, we start with the hypothesis that the difference between the proportion of success in sample 1, P1, and the proportion SP of success in sample 2, P2, is due to fluctuations of random sampling. In other words, we take the null hypothesis as H0, P1, P2, and for testing the significance of difference, we work out the test statistic as under. Pause the video to look at the formula, where P1 is equal to proportion of success in sample 1. P2 is equal to proportion of success in sample 2. Q1 1 P1. Q2 1 P2 N1 is equal to size of sample 1. N2 is equal to size of sample 2 and is equal to the standard error of difference between two sample proportions asterisk. Then, we construct the rejection regions depending upon the Ha for a given level of significance, and on its basis we judge the significance of the sample result for accepting or rejecting H0. We can now illustrate all this by examples. Hypothesis testing for comparing a variance to some hypothesized population variance. The test we use for comparing a sample variance to some theoretical or hypothesized variance of population is different than z-test or the t-test. The test we use for this purpose is known as chi-square test, and the test statistic symbolized as 2, known as the chi-square value, is worked out. The chi-square value to test the null hypothesis with h0 to 2 worked out as under SP. Pause the video to look at the formula, where 2 is equal to variance of the sample. 2 is equal to variance of the population, and 1 is equal to degree of freedom, n being the number of items in the sample. Then by comparing the calculated value of 2 with its table value for n1 degrees of freedom at a given level of significance, we may either accept h0 or reject it. If the calculated value of 2 is equal to or less than the table value, the null hypothesis is accepted, otherwise the null hypothesis is rejected. This test is based on chi-square distribution, which is not symmetrical and all the values happen to be positive. One must simply know the degrees of freedom for using such a distribution asterisk. Testing the equality of variances of two normal populations. When we want to test the equality of variances of two normal populations, we make use of f-test based on f-distribution. In such a situation, the null hypothesis happens to be h0 to 1 to p1 and to representing the variances of two normal populations. This hypothesis is tested on the basis 2 of sample data, and the test statistic fi is found using 2 and 2 the sample estimates for 2 and 2 respectively, as stated below. 2. Pause the video to look at the formula. While calculating f, 2 is treated to, which means that the numerator is always the greater variance. Tables for f distribution have been prepared by statisticians for different values of f at different levels of significance for different degrees of freedom for the greater and the smaller variances. By comparing the observed value of f with the corresponding table value, we can infer whether the difference between the variances of samples could have arisen due to sampling fluctuations. If the calculated value of f is greater than table value of f at a certain level of significance for n1 1 and n2 2 degrees of freedom, we regard the f ratio as significant. Degrees of freedom for greater variance is represented as V1 and for smaller variance as V2. On the other hand, if the calculated value of f is smaller than its table value, we conclude that f ratio is not significant. If f ratio is considered non-significant, we accept the null hypothesis, but if f ratio is considered significant, we then reject h0, i.e., we accept ha. When we use the f-test, we presume that I, the populations are normal. 2. Samples have been drawn randomly. 3. Observations are independent. And 4. There is no measurement error. The object of f-test is to test the hypothesis whether the two samples are from the same normal population with equal variance or from two normal populations with equal variances. F-test was initially used to verify the hypothesis of equality between two variances, but is now mostly used in then context of analysis of variance. The following examples illustrate the use of f-test for testing the equality of variances of two normal populations. Hypothesis testing of correlation coefficients asterisk. We may be interested in knowing whether the correlation coefficient that we calculate on the basis of sample data is indicative of significant correlation. For this purpose, we may use In the context of small samples, normally either the t-test or the f-test depending upon the type of correlation coefficient. We use the following tests for the purpose. A. In case of simple correlation coefficient, we use t-test and calculate the test statistic as under. T equals to, with n2 degrees of freedom or yx being coefficient of simple correlation between x and y. This calculated value of t is then compared with its table value, and if the calculated value is less than the table value, we accept the null hypothesis at the given level of significance and may infer that there is no relationship of statistical significance between the two variables. B. In case of partial correlation coefficient, we use t-test and calculate the test statistic as under. T equals to, with nk degrees of freedom, n being the number of paired observations and k being the number of variables involved, Rp happens to be the coefficient of partial correlation. If the value of t in the table is greater than the calculated value, we may accept null hypothesis and infer that there is no correlation. C. In case of multiple correlation coefficient, we use f-test and work out the test statistic as under. F equals to, where R is any multiple coefficient of correlation, k being the number of variables involved and n being the number of paired observations. The test is performed by entering tables of the F distribution with V1 is equal to k, 1 is equal to degrees of freedom for variance in numerator. V2 is equal to n, k is equal to degrees of freedom for variance in denominator. If the calculated value of f is less than the table value, then we may infer that there is no statistical evidence of significant correlation. Limitations of the tests of hypotheses. We have described above some important tests often used for testing hypotheses on the basis of which important decisions may be based. But there are several limitations of the said tests, which should always be borne in mind by a researcher. Important limitations are as follows. I. The tests should not be used in a mechanical fashion. It should be kept in view that testing is not decision-making itself. The tests are only useful aids for decision-making. Hence, proper interpretation of statistical evidence is important to intelligent decisions. 6. 2. Tests do not explain the reasons as to why does the difference exist, say between the means of the two samples. They simply indicate whether the difference is due to fluctuations of sampling or because of other reasons, but the tests do not tell us as to which are the other reasons causing the difference. 3. Results of significance tests are based on probabilities and as such cannot be expressed with full certainty. When a test shows that a difference is statistically significant, then it simply suggests that the difference is probably not due to chance. 4. Statistical inferences based on the significance tests cannot be said to be entirely correct. Evidences concerning the truth of the hypotheses. This is especially so in case of small samples where the probability of drawing erring inferences happens to be generally higher. For greater reliability, the size of samples be sufficiently enlarged. All these limitations suggest that in problems of statistical significance, the inference techniques, or the tests, must be combined with adequate knowledge of the subject matter along with the ability of good judgment.